Okay, so guys, for part A we got the value of intensity, right? For question, example for part A we got intensity I1 equal to 0.71 watt per meter square. B, we are supposed to find at what distance R2 the intensity would be 1/4 of the intensity that we found in A. So so here in place of I2 we can write as P, right? Power divided by 4 pi R2 square, which is equal to 1/4 times I1. 4 and 4 are common on both sides, we can cancel those out, and then after that we could just rearrange this, right? So R2, I'm just taking this R2 over here, so P, and then bringing this I1 down here, so it turns out R2 equal to P divided by pi I1. Now if I take out this square, then it becomes the square root goes on the other side, and then that gives us this here, right? So P divided by pi I1 is square root of that, and then after substituting the value of the power, which is 80 for pi, it's just constant, and then I1 was 0.71, we get close to 6 meter, right? So that makes sense because the intensity is going to reduce by 1/4 of the value at this distance, right? So further away the intensity is going to be lower, okay? Alright guys, so that's the example for sound intensity. Okay, so okay. Okay guys, so source, so you have a sound source, right? And then it's producing a sound, but then let's say it's also, and then there is an observer, okay? So for example, there is a speaker that's coming towards me. I'm sitting here and it's coming towards me, and then it comes here near me, and then it passes away, right? So what happens is there is going to be a difference in the frequency of the observed frequency, okay, of the sound that I perceive basically. Let us say, so here I have some of these, here I have a diagram here, it's like this. So here is, I got the source here, source is here, and then there is this, it's producing some waves. So the source is moving, okay? Let us say it's like this. Let's say source is moving, and then the source as the speed is smaller than the speed of the wave itself, okay? Meaning, you have like I'm carrying, or it's like someone is carrying a speaker and walking towards me. So the speaker is, producing a sound. It has some, sound has some speed, but then the movement also, the motion of the, portion also has some speed, right? So let's say the speed of the source is smaller than the speed of the wave. Then what happens is, the wave are going to look something more like this, and then kind of like this, okay? So here is the, so you see, it looks like the frequency is kind of, bigger here than this side, right? So the same thing happens. So if we have, several sound waves, if we add them like together, and then they are going to produce a very large sound, okay? If we have several sound, right, so not just one source, many other sources, it's going to produce a very large sound. That is called sonic boom. Alright, so when could this happen in real life? I mean, when really sonic boom does happen every time the plane is taking off, or whenever the rocket is launched. Okay, and there are other cases also. So this thing here, keep this diagram in mind, and we are going to talk about a little bit of other things here. I don't know if you guys can see this figure. I think it is better for me. Maybe. Let me try to draw it over here. So this case was for the, there is the source that's moving with the speed smaller than the wave speed, okay? So at this part, it looks like, the frequency is higher than this side. Let's say if we have a B source moving with the V wave, okay, the speed of the wave, then it's going to be something like really like this. So basically concentric circle here. So here, all of them, they kind of go from like concentric, so they should not be intersecting concentric circle, and then just like that, right? So see, this is now one point here when the speed of the source is equal to the speed of the wave, right? So the wave front and the source, they are at the same point. Then this diagram is a little difficult to draw here, so I'm just going to show the other one here. So when the source is moving much faster than the wave, then you see this wave is kind of left behind, and the source is way at the edge here. Okay. So those are the different cases. Now. So one interesting aspect of sound in the wave is called Doppler effect. So what is Doppler effect is really that perceived change in the frequency when the source producing the sound is moving. Okay, it is approaching or receding from the observer is called Doppler effect. It was a I don't know how did it Johann Doppler. I know the Doppler, I can say correctly, I don't know how you pronounce this. Johann Doppler, he predicted about Doppler effect in 1842, and then he actually proved it in 1845 in an acoustic extravaganza that it's a real effect, okay? So there are there are 4 different cases for Doppler effect that, we'll be using. So let's say we have an observer, let's say this is the, sound source, okay? Really, you can make a circle here, sound source, and then let's say the observer here, this guy, this is moving towards the source, okay? And then this, observer is moving toward, right? It's moving with some speed, okay? And then we have this source, it is producing some sound of a speed v. Then the observed frequency f naught is given by this equation here, where f naught equal to fs times 1 plus b naught by v, where fs is the source frequency. So this one, source also has a frequency, right? So fs is produced by this one, f naught is the observed frequency, v naught is the speed of the observer, and then v, so this guy moving with the speed v naught, okay, this way, and then v is the speed of the wave that's produced. So this is the equation. So f naught is basically fs times 1 plus v naught over v, okay. So this is when this observer, imagine there is this speaker in your room, you are moving towards the speaker, okay, then you would find the frequency that you observe is given by this equation, all right here, okay, because as you are moving towards the source, right, so this quantity is going to be bigger, right, Now, the other case is when observer moving away from the source. So imagine yourself, instead of going towards the source, now you would go to the other direction, this way. You move with the speed v naught, okay? Then the equation is just, all you have to do is just change this with the negative sign here. Alright? F naught equal to Fs times 1 minus v naught by v. Makes sense, right? The observed frequency is going to be what? It's smaller than the frequency of the wave here, right? Because you're going further away. Alright, so that's the case. There are two more cases. So here, one thing is at stationary or rest, right? Source is at rest here. Only you are moving it. The object that's producing sound is not moving, okay? Now, another case is source moving towards observer. So this time you are staying at rest, and then someone is carrying a speaker and then moving towards you, basically, okay? So source moving towards speaker. Source moving toward observer. Observer. Then the frequency is given by F naught, the observed frequency. The frequency you observe is given by F naught equal to Fs 1 divided by 1 minus V is by V. Here, F naught is observed frequency, Fs is the frequency of source, right? 1 divided by 1 minus Vs is the speed of the source, because now source is moving towards you, right? Someone whoever is carrying a speaker is moving towards you, so that's Bs. Divided by V is the speed of the sound, okay? So this is the thing. Here V is the speed of the sound, Bs is the person that's carrying, that's their speed, okay? V itself is the speed of the sound that is produced. So speaker sound speed is V. Person who is moving, their speed is Bs. Alright? Now let's say this source is moving away, then it turns out we'll just replace this with the positive sign here. So equation is just let's see. Equation is just F naught equal to Fs 1 over 1 plus Vs by V. Okay? Alright. Do you guys see something here, right? Alright, I'm not gonna tell that. I think that will confuse you. So anyway, so we can combine these two equations, right? So if we put this together, we could really write general equation, and that's gonna be something like this: F naught equal to Fs 1 divided by 1 minus Vs by V. Okay? So, plus sign, minus and plus sign. So this is a general, putting both of those equations together. Minus means indicates source is moving toward, okay? This is given by this negative sign here. If this source is moving away, then it is given by the positive sign, okay? So away is positive, towards has that negative sign there, okay? So that's the equation for determining frequency, Doppler shift frequency, okay? So really the observed frequency. Okay, so here is an example question. So the example says, a car traveling at 20 meters per second blows a horn at a constant 600 hertz. Determine the frequency heard by a stationary observer as the car approaches and recedes. So here a car traveling at 20 meter per second, right? So Vs, right, speed of the source is what? 20 meter per second. So we can, if you want, you can also make a really small, diagram here. I think this would be probably helpful. That's my. Oh, that looks like a band, guys. But I think that's okay. Okay, I'm gonna make a car. That's blowing a horn, so sound coming out there. Okay. And it's traveling at 20 meters, so it has the speed Vs. It's moving that way, right? At a frequency, constant frequency, if S is 600 hertz. Okay. So we are also given if S equal to 600 hertz. Determine the frequency heard by a stationary observer. So let's say this is you. I mean, representation of you, not you. Okay, you're sitting here, stationary, and then determine the frequency heard by you. So if not equal to what? Okay, as this car approaches you and then goes away. So there are two situations, right? So let's call this if not. I don't know. Let's say call. If not, let's call one. If not, let's call another. If not, dash. Okay, dash is what? This is for away. I'm writing dash just to make a distinction between when the car approaches to the person. Let's call that observed frequency as. If not, when it goes away, to say that away, let's put a dash here in the equation. Okay, if not. So we have two different cases, right? Please use the speed of the sound. V equal to 340 meter per second. We have the 300. You could, 340 meter per second. Okay. And then please take a few minutes to work on this and see what you get. Okay, guys. So how do you find what's the F naught? So you guys remember, I'm going to erase this one here too because I need some space. Okay, guys, so were you able to, work out through this problem? So how do we find the observed frequency F naught, right? If you remember, when source is moving towards observer, we can write F naught as what? F naught equal to F is 1 divided by 1 minus what? V is by V, right? Remember, negative sign means away, okay? Wait, we said away toward as a positive, source moving, no, this is source moving toward observer is a negative. Yes, this is correct. So, okay, so if we use the value given to us, what is Fs is 600 hertz, 1 divided by 1 minus Vs is 20 divided by V is what? 340. If you do the calculation, what do you get here? So you should get the value about 638 hertz. Okay. Now for this F naught, right, dash, what do you need to do? Everything same. What you have to do is use the positive sign. Okay. So I'm gonna let you guys work on that and find the answer. The answer should be 567. Okay. So F naught dash is 567 hertz. This is not exactly close to 567 hertz. Okay. All right. So with this, we are done with this chapter and traveling wave and sound. In the next lecture, we'll start with the new chapter. Okay. All right, guys. Bye bye.